All right. So I was talking about lasso and ridge regression regularization techniques. And what was the issue? See, as I told, your linear regression algorithm may face an issue of overfitting. Okay. So linear regression do have overfitting issue. And this is because you might be training your model, linear regression model, over correlated or co-linear features. That means you are using multiple features, you are performing multiple linear regression, and you faced a problem of overfitting. So what we have to do is, the equation says y equal to beta naught plus beta 1 x1 plus beta 2 x2 and so on. If your model is overfitted, definitely these two things, correlated and collinear, that means your features, they do have relationship. Okay, they do have relationship among each other, which is not considered, which is not an assumption. We should have a minimum correlation between the features. But if we are having high correlation between the feature, then there is an overfitting in the model. Okay, so it has been told in regularization regularization that anyhow you have to deal with this overfitting. So obviously I need to eliminate, or I need to reduce the power of features. Power doesn't mean to the power, no. Power is a general term. I need to eliminate the features, or either I need to reduce their impact. Power, as I said, impact over the model. I need to eliminate, reduce this thing. So how should I do? What I have? Yesterday, I told we are having cost function is equal to summation predicted minus actual ka whole square by n. This is what we are having. And I also told that in order to deal with overfitting problem, you have to penalize your model. You have to add a penalty. And we are having two kinds of penalty, L1 and L2. This will be followed up in deep learning also. Okay, these penalty terms are applicable ahead too. Okay, fine. So I want to penalize. How? What should be done? So the maths says that L1 is the sum of coefficients. I told yesterday also. L1 is the sum of coefficients. L2, you can say square of the coefficients. This is what you can say. sum of the squares of the coefficient. Okay, I think I should put root also, because L1 is less so, L2 is rich, this is Manhattan distance, this is Euclidean distance. So let's put root also. And the penalty says that when you are writing your equation, beta naught plus beta 1 x1 plus beta 2 x2, you have to divide this equation by the regularization terms. Like, I will be dividing L1 to each of the coefficient present in the equation. Now, same thing I can do with ridge also. I can divide. Okay, like this I can perform. Okay, this can be done. Okay, so the ratio will get a minimum value. This ratio will get a minimum value, and I told already that I want to either eliminate the feature or either I need to reduce the impact of the feature. The reduction or elimination can only be done by dividing with some value. Okay, so let me share my entire screen and do have some discussion related to what's more said on these techniques. So, rich, less so are popular regularization techniques used to reduce the errors in linear regression. That is why now I added penalty into the cost function. Cost function is an error. I want to reduce the error. Error reduction means the overfitting which was happening. I need to take care of that. Error means during test. During test, error is more. I need to reduce those errors. Okay. So getting started with Ridge, it is also used to prevent overfitting. That's what the main purpose. As like less so, it is represented by L2 or L2 norm. Norm is normalization also. Normalization. Norm is normalization. It's either said regularization or normalization. That's what we can say. And the main aim is this only, to reduce overfitting. Both L1 and L2, they are designed for this purpose. If you see graphically, this is a best fit line. This graph is of a best fit line. We are having a training data. Yesterday also I asked that between whom you are making this plot, between whom you are doing this thing. If it's 2D, we are going to build a linear regression a model that will be the best fit line when all the training points will come over this line. Okay, when all the training data points will come over this line. Now, training data come over this line means what? We do have X and Y. X is training feature, Y is your target. So we are keeping X on this axis and Y on this axis. We are assuming a linear relationship between them. Okay. And if this thing happens exactly that the points come in a line, then it is best fit. Then it is best fit. Who made this line? Who made this line? What is the criteria of making a line? Can you tell me what is the criteria of making this line? Yes, I am just having this equation. By my calculations, I found the value of m and c. These are the coefficients you very well know. Okay. And then, okay, this is y equal to mx plus c by my own working by solving this cost function which we have done the entire derivation. I found m and c. After getting m and c, I can calculate y prediction by putting the value of m and c here, and x I can take. So this is the x, and if the points, the predicted points which I calculated, they are coming in a same line. Okay, they are coming here in this line. I can have a comparison. That means if this is x and y, let us make between x and yp also. Okay, x and yp also. So the points are coming on a line, that means no error. It's a best fit line. However, the best fit line is a line passing through all the training data points, all the training data points. And the cost function is 0. That means predicted and y both are same. In the plot only I show both are same. See, they are coming over a line now. So initially, if this is what I have drawn between x and y as per my equation, and this is what, after getting m and c, I calculated the prediction. Okay, so if they are coming, if all the training points, if the best fit line is the line passing through all the training points. Okay, so you have built the training points, you got the points like this, and if you make a line, it should cover all of them. If it does, then it's a best fit, else it's not. This means that the training data is very well good accuracy, but if in case data doesn't follow, then it is said to be an overfitting. But with the test data, this is how you got the points. This is how you are available with the points. That means this is your x, this is your y. For this x, you got this y. For this x, you got this y, and so on. Few points, if you make a line, few points will be captured. So we are saying that this is a line with errors. This is a line with errors. And if there are many errors, if there are many errors, then you have to take some step to reduce the errors. If there are many errors, means the points are not coming on the line; they are coming far away from the line. Okay. So the question is that there are many things which can come into the mind. The point is, sir, this is x, this is y. If I draw a plot between them, a point can be here, 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 here. Anywhere the point can be present. Here also, here also, here also, here also. So I just make a line. I just make a line. Okay. For example, this line I made, 3 points are coming. For example, this line I make, 3 points are coming. For example, this line I make, 2 points are coming. But not all the points are coming on any of the line which I have drawn. That means if I consider this as a line, the points present here are error, and these points are also error points. It has been said that all the training points should be captured by the line. So if this is x, this is y, and if you plot between x and y, okay, if you plot between x and y, for example, these are the points coming, and if you make a line and all the points are captured by the line, this is the best fit line. But beware, you may be trapped in an overfitting. This is training data. With testing data, it's not mandatory. Because with this training data, you have calculated M and C. Next time, if you put M and C to perform the prediction, it may happen that YP which you are getting, they will be some here, some here, some here, some here, some here. So they are not captured by the line. That's what shown. That's what it's shown. Red ones are the error. They are. This is the distribution, and you are trying to make a line, but unfortunately, less points are covered. Okay, so that is the case. Fine. That's the reason we are dealing with regularization or normalization technique, that is ridge and the lasso. And ridge works by adding penalty to the cost function called as regularization. It prevents the model from overfitting by penalizing the large coefficients. By penalizing the large coefficients. What it means, large coefficients? Let's see. The regulation parameter determine how much model should penalize. It determines also how much penalty needs to be done. By increasing the regulation parameter, the coefficient can shrunk to zero. Okay, in this paragraph, many things are written. They are saying that you have, this is your cost function. I have written multiple times, predicted minus actual का square का summation divided by n. This is cost function. They are saying that add a penalty. Lambda is a hyperparameter. It is called as your regularization coefficient. Okay, it's a hyperparameter. It's a parameter actually. Okay, so it is a regularization hyperparameter. It controls how much penalty you want to eh, put on the model. It controls. So slope square, you very well know. I just told you. Slope square. This is the slope. Just calculate square of it. So you will be getting beta square plus beta 1 square plus beta 2 square. This is what slope is for ridge. Okay, that's the slope for ridge. For lasso, this is the slope. Lambda is a regularization parameter. How much penalty you want to induce? It will be having some range of values. Either it's like between 0 to 1, something like that. Because if you induce more penalty, your coefficient will shrunk to 0. This will eliminate the feature. Okay, I will be coming on that. So in case of ridge, it is saying slope square. If lambda is 0, the cost function of ridge is equal to the linear regression. Obviously, if this will become 0, this will be the cost function of linear only. If even adding hyperparameter to the original cost function, the training accuracy won't improve, then we can change the value of lambda and try to find the best hyperparameter. Okay, if your scores are not improving, then you have to change also. Okay, so that we can look out it can improve or not. Okay, so adjust the value of hyperparameter. So the cost function is changing after adding hyperparameter. The model will also change the best fit line. Okay, so accordingly, the line will also change. If you change the value of lambda, the line will also start changing. So how I can write this entire equation? How I can write this thing? It can be written as like this. For ridge, you can write the equation for cost function as summation of yp minus y का whole square divided by n plus lambda into slope का square. It can be also written as summation yp minus y का whole square by n plus lambda into beta naught का square plus beta 1 का square. Okay, that's it. Let us suppose just we are having y equal to beta naught plus beta 1 x. That's it. Okay, just suppose this thing we are having. Okay, got it. So this is your cost function for ridge, and everything can be controlled by lambda. This is control. If 0, then it is like linear, and if it is 1, that means high penalty. Because of high penalty, it may happen that your coefficient may tend to 0, because you are dividing this penalty with the coefficients. So if this value is high, then definitely there is a chance that a ratio can become 0. And if it becomes 0, then 0 multiplied by the feature, it will become 0. So it will be eliminated. Okay, fine. What's said? Huh. The slope is inversely proportional to lambda. That's what it is saying. The slope is inversely proportional to lambda. This means that if the hyperparameter increase, the slope is decreased. Okay, that's a general relation between the slope and the value of lambda. Okay. In Lesso, we do have the same thing. It is called as L1 norm या L1 regularization. But okay, both L1 and L2 are designed to reduce the overfitting. But you have to remember one thing. L1 can reduce the features. Very important. L1 can drop the features. It can reduce the features. It is dimensionality reduction technique. It is dimensionality reduction. The task of L1, L2 both is to prevent overfitting, but L1 can reduce the features. How? It can make the ratio tend to 0, due to which if a 0 is multiplied to any feature, they will become 0. For example, if you are having y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4, and if you are applying L1 regularization, it may happen that your x2 and x4 can be dropped. Then you are left with only y equal to beta naught plus beta 1 x1 plus beta 3 x3. So L1 reduces the feature. It is a dimensionality reduction technique. It is used for feature selection. Remember, you may be asked which technique is a feature selection technique. Okay. So less so L1 is feature selection. L2 doesn't do that. L2 doesn't do. L2 doesn't reduce feature. L2 is not feature selection. No. L2 reduces the impact of feature, but it never reduce the feature. Rich never reduce feature. It prevents overfitting. L1 also prevents overfitting, but it is extra. It is feature selection technique also. Dimensionality reduction. It can reduce the features with preventing. But rich don't do that. Rich prevents overfitting, it reduces the impact of features which are giving overfitting, but it keeps them in the equation. It never drops. This is your cost function for less so. Again, the same, only the thing is, in ridge I was having slope square, in less so I am having slope because it is Manhattan. Na? It is Manhattan distance. So I can write for the less so, the cost function for less so. It will be summation of yp minus y ka square divided by n plus lambda beta naught plus beta 1. This is less so. Okay, but remember, less so is feature selection. It can reduce features. So, whatever be the features we are left, they will be selected. And those who are reduced, they are over, they are dropped. Okay, they are dropped. Fine. So, what's next? Okay. Again, lambda and the slope, they are inversely proportional for this also. Okay. The difference between ridge and the lasso. What is the difference between them? That's what I told. Ridge and the lasso. They both shrink the coefficient, reduces the impact of coefficients. Okay, impact of coefficients, ultimately it will multiply with the feature, so feature will be impacted. Rich can reduce all the coefficient to a small amount. Okay, it can reduce the value, but less so can reduce some feature more than others, and hence it can completely eliminate those features. Okay, rich impact come karta है, it will reduce the impact, but less so can drop completely eliminate the feature itself. That is what is called as feature selection. Okay, fine. Now, all right, so these terms I told, reg is L2 normalization. Okay, it encourages the coefficient to be small, but do not force them to exactly zero. Okay, so never, in rich, never, coefficient can be small, but they cannot be zero. It doesn't force them to be zero. However, less so, the full form of less so is, see, ridge regression is also known as Tikhonov regularization. There is a name for it. L1, less so, its name is least absolute shrinkage and selection operator. That is a full form of less so. Least absolute shrinkage. Okay, least absolute shrinkage and selection operator. That is the name of less so. Okay, fine. L1, fine. It forces the coefficient to become exactly zero. Okay, now the key differences are mentioned. Rich uses L2, less so uses L1. I already told. Euclidean, Manhattan. Less so can lead to sparse solutions with some coefficient exactly zero. Okay, it introduces sparsity in the data. Value of some coefficient, it will make zero. However, rich shrink, but it will not make zero. Multicollinearity. Rich can handle multicollinearity well by reducing the impact of correlated variables. Less so arbitrarily select one variable from a group of highly correlated predictors and it drop it. It arbitrarily select the variable. See, now there is an issue. There is an issue. What happened? See, let us suppose, again I am writing equation beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 and so on. It has been told that less so arbitrary select. For example, x2, x3 and x4. x2, x3, x4 are correlated. Let us suppose this thing. Okay. Out of these, okay, x2, x3 and x4, okay, they are correlated. And if I check the relationship with the target, why? Let us suppose x2 is showing high correlation with the target. So it is required that x2 should be present while model training, because x2 is giving more variance to the target. It is related to the target. But what is the statement written for less so? The statement says that less so arbitrary selects. It can select x2, it can select x3, it can select x4 to drop. Now, if if L1 drops x2, it is a big loss. Why? Because x2 was in good correlation with the target. But what L1 did, what Lesso did, it found that these three are correlated. So let us drop x2. It arbitrarily selected x2. It dropped it. And because it dropped it, so we lose a feature which is which can put a good correlation with the y, which can help in prediction of y, but we lost it. That is one of the drawback of Lasso because it arbitrarily selects out of the correlated features. That is the key difference. Okay, Lasso, the rest interpretable. That means okay, both are interpretable. We can interpret. That's not a deal. We can solve them. Okay, like linear regression was also not complicated. They are also not complicated. Okay, we can solve them. So Lasso ability. Only the thing is, it produces sparse data. Okay. However, we don't have sparsity in rich. Okay, that's the difference. Fine. Okay, equations I've already told you. Okay, so these are the same thing written. Okay, all right, same thing. Here is some maths which I have already shown you. Okay, so this is your sum of the coefficient means less so L1. Okay, and you are writing with the cost function of linear regression plus penalty. This is less so. Okay, so if we want to optimize less so, initially beta is an arbitrary value. For each value of beta, update still the less so proximal operator. Okay, it's not here. It is an arbitrary value. Repeat these steps until we are not converged. That means for each beta j, update it using Lasso proximal operator. This is Lasso proximal operator, some mathematical equation mentioned. It's very in depth. Sine of theta j equal to max of theta j minus lambda by n, comma 0. So max of theta j minus lambda by n or 0. Whoever is maximum, just return that with a sign, positive or negative both. Theta j. What is theta? Theta is a parameter. Theta is a feature, I guess, not a parameter. It's a feature. Theta is a feature because beta is a coefficient. So theta is a feature. So theta minus lambda by n. Lambda, you very well know, it's regularization parameter. Capital N may be number of data points, sample. So there might be some loop which is initiated here that is solving this equation. We will not go into that much deep. It just came into my notes. Okay, we'll just follow the regular formula, because this may make the things complicated, not as such required. Okay, the kind of maths which we know is we have to divide, we have to divide, the regulation says that divide the L1 or L2. Okay, divide L1 and L2. Okay, keep them in denominator with uh, below coefficients. That's what we have to do. Okay, and you can adjust the value of lambda. That's what you can do. Rest, going through deep and what kind of mass was assumptions they are taking, that's quite complicated. We're not dealing with that right now. We got to know what's the basics behind it. Okay, so we are having some advantages related to that, and I do have some code also. If I show you the code, this is the code for Lesso and the rich. I took Lesso first. So Lesso is present in linear model only. Polynomial, which I taught yesterday, that was not present. Polynomial is just we have to assume, we have to convert the features into polynomial value. Lesso is present in linear model. Okay, and we are making a synthetic data here. Okay, just a synthetic data we are making. Just a second. क्या कह रहा है मनोज?
छोटू तेरी क्लास है तो यार 2 मिनट आ जाना, मेरा गद्दा रखवा देना यार।
हाँ आता हूँ। हाँ
है ना, कितनी देर से क्लास
आ
है?
रहा हूँ मैं 5 मिनट ना।
ठीक है।
Okay, so here I just create a synthetic data with 100 samples. That means 100 rows, one feature. Okay, I'm having only one feature, and 100 rows are there, and random values will be available in that. Okay, I split it, performed train test split. I took Lesso model, alpha equal to zero point 0.1. Okay, so alpha is your regulation parameter. I took their lambda, here it is alpha. So don't get confused. Alpha and lambda both are same. Either you can take alpha, either you can take lambda. Not a worry. Okay, so I took this alpha zero point 0.1, and yes, this is my Lesso model. I fit my data into the Lesso model. Then I perform the prediction from it, and I printed the scores. And then I perform the plotting between X test, Y test, and X test and Y prediction. I made a plot, and this is how the plot looks. You can see actual and predicted, they are overlapping. Okay, so between whom the plot is made? X test and Y test, X test and Y prediction. I also told previously that if you make a plot, remember, I have shown them separate X and Y and X and YP. Now you can combine them in both. And by performing this, I'm getting such kind of points. Okay, that's what I'm getting. So red and blue are overlapping. So I can have a best fit line here. And obviously I have applied the regularization parameter, so there will be no overfitting. This is what I'm getting. Okay, that's what I'm getting. And this is the residual plot. Residual means predicted minus actual. That's what the residual is. Okay, so this is a residual plot. Okay, fine. So you can see the residual y predicted and y predicted minus y test. Okay, so prediction and prediction minus actual. This is residual, and this is y predicted. So this is residual. We can make scatter plot between them also. That's what been shown. Residuals. Okay, so this is about less so. We do have about rich too. We have the concept related to elastic net, which is a combination of L1 L2 both. Okay, so in the next class we'll study L2 code. We'll find what are the advantages, what are disadvantages, few more things, maths if it is required I will include for them. Okay, and then we are having elastic net, which is a combination of these two, L1 plus L2, which is using the power of both the regulation technique, L1 and L2. Okay, so I'll be discussing ahead in my next class. Okay, I hope you understood the lecture today, isn't it? You got an idea about this regularization. Okay, fine. All right, let me stop the recording.